Okay, learning target number 3. So we're going to be looking at free body diagrams and determining, are we looking at a dynamic situation or a static situation? So a dynamic problem is when the net force is not equal to 0. Okay? And so if that net force, the sum of the forces, equals mass times by acceleration, if the net force or the sum of the forces does not equal 0, then the acceleration is not going to be 0. In a static problem, we're doing the opposite of that. When the net force is 0, we call that static, and so then the acceleration must be 0 as well. Okay? Now, just a reminder about vector addition. So if we have a free body diagram and we have these 3 forces acting on this object, we can do the sum of the forces graphically by adding those together. Like we could take A, okay, and then we could add B, and then we could add C. And finally, our resultant is from the tail of the first to the tip of the last. Okay, so there's our big resultant vector. Okay? So we can graphically do it that way, or we can break it up into x and y components and add all of those up. So that's what we're talking about here. Our overall resultant is going to have an r sub y and an r sub x. Okay? And all the r sub x is the x components of A plus B plus C in this situation, because we had 3 vectors involved. And then the r sub y, well, that's just going to be A sub y plus B sub y plus C sub y. And we use our trig to find these different components there. Okay, let's try a practice problem. What is the sum of the forces in the x direction and the y direction for the following free body diagram? Then define the resultant vector for the free body diagram, magnitude and direction. Okay, so we want to know the sum of the forces in the x direction and the sum of the forces in the y direction. Okay, let's see what that is. X direction. We don't have any vectors in the x, so the sum of the forces in the x direction, that's just going to equal 0, right? Because we didn't have any forces. But in the y, it's different though. In the y, we have a positive force of friction, which is 60 newtons, and then we're going to add that to the negative 150 or minus 150, or force due to gravity. Okay. And that does not equal 0, right? Because our force of friction, that's 60 newtons minus the force due to gravity, 150 newtons. Okay. Now let's go through and talk about sig figs because we're subtracting. So our 60 here minus the 150, well, we have 1 digit after the decimal place there, okay? And then we don't have any digits after the decimal place here. And so our answer is not going to have any digits after the decimal place. So the sum of the forces in the y direction, all that, is going to equal negative 90 newtons. Okay. Now, let's draw that resultant vector. So here's the tail of my resultant. I'm not going anywhere in the x direction. And then I'm going down 90 newtons. Okay, so define the resultant vector for the free body diagram. Well, there's our resultant vector. Example problem number 2. Let's see where we're at time-wise. Okay. What is the sum of the forces in the x direction, y direction for the following free body diagram? Then define the resultant vector for the free body diagram. Okay, so let's look at the sum of the forces in the x direction, and then we'll look at it for the y. So in the x direction, we have a positive force of tension, and we have a negative force due to friction. So the force of tension is 30 newtons minus friction, which is mu k normal force, and the normal force was 25 newtons. So this coefficient of friction is 0.4, and then I'm going to times that by the normal force, which is 25. Okay, so this is 10 newtons. So 20 newtons overall. So the sum of the forces in the x direction are equal to 20 newtons. Okay. Now in the y direction, we have a positive force normal minus our force due to gravity. Force normal is 25 newtons minus the force due to gravity, which is 15 newtons. And so that's sum of the forces here is equal to 10 newtons. And so sum of the forces in the y equal 10 newtons. Let's draw what this resultant or sum of the forces is. So we have a positive 20 in the x, okay, right? So that's the sum of the forces in the x. And then we're going to add that to our positive 10, sum of the forces in the y. And so our resultant is right there. This is sum of the forces in the x. Then we have some resultant, right? So let's use Pythagorean theorem to figure out what that resultant is. So we have a squared plus b squared equals c squared. Or my resultant, this, which is just the sum of the forces in general. Okay. That's going to equal the square root of the sum of the forces in the x squared plus the sum of the forces in the y squared. So I'm going to plug that in. So the square root, sum of the forces in the x, well that was 20 newtons, plus sum of the forces in the y, that was 10. Okay, looks like we're dealing mostly with 2 sig figs, so that'd be 22 newtons. Okay, good. We know the magnitude, but not the direction. We need to figure out what this angle is there. Okay, so remember that tangent of that theta is going to equal opposite, which is sum of the forces in the y, over adjacent, sum of the forces in the x. Okay, or theta is going to equal tan inverse, sum of the forces in the y over sum of the forces in the x. Okay. So let's plug that in. So we're going to go tan inverse. Sum of the forces in the y was 10. Sum of the forces in the x was 20. So this angle is 26. Round that up to 27 degrees. Okay. Okay, I think we have time for at least starting the next practice problem. So what is the sum of the forces in the x direction, y direction for the following free body diagram? Define the resultant vector for the free body diagram. Okay, so we're at an angle here. So this is not a vector, this is just to show you here's the x-axis, and this angle is 60 degrees from that x-axis, and it's a force due to tension. So we have a force due to tension in the y, and we have a force due to tension in the x. We can break that up into its x and y components there. Okay, which is nice because then we can observe it with the x and the y. So I'm going to start with that. I'm going to solve for the force due to tension in the x and then the force due to tension in the y. So here is the angle. Opposite from that angle is the y. Adjacent to this angle is the x. The hypotenuse or magnitude is the 75 newtons. So remember our trig functions, force due to tension in the y direction, that's opposite. So it'll be the hypotenuse, 75 newtons, sine theta, 60 degrees. Okay. So that will give us the force due to tension in the y. And then force due to tension in the x. X is adjacent, so it's going to be the hypotenuse, 75. And then it's going to be cosine theta. So force due to tension in the x will give us something. Okay, so I'm going to plug those numbers in. So we're going to take 75 times by the sine of 60. Make sure your calculator is in degrees. Okay, so we have 65 newtons in the y, and then 75 cosine 60. That is 38 newtons in the x. Okay, wonderful. So now that we know the x and y component of this, we can do the sum of the forces for everything in the x and the y. Okay, so sum of the forces in the x direction. We have this force due to tension in the x, and that's our only force in the x, right? So the sum of the forces, well, that's just the force due to tension in the x direction. And that we know is 38 newtons. So the sum of the forces in the x direction is just 38 newtons. Okay. Now let's look at the y. We can probably put it in here. Sum of the forces in the y. Well, we have a positive force due to tension in the y. Okay, and we're going to add that to the negative force due to gravity. Okay, we'll see what that equals. So the tension in the y is 65 newtons minus our force due to gravity, which is 35 newtons. Okay. So we end up with sum of the forces in the y direction going to equal 30 newtons. Okay. So we found the sum of the forces in the x direction and the y direction. Now we're going to define the resultant vector of the free body diagram.